Welcome to the next video in the Combinatorics series. We're discussing Chapter 1, Enumerative Combinatorics, and specifically in this video we will discuss problems 1-110 through 1-113. Problem 1-110 asks us to find the number of distinguishable permutations of the word Mississippi. To begin with, let's be clear what a distinguishable permutation is. If we swap the letters M and I, this is a distinguishable permutation. However, if we take any two instances of I and exchange them, this is not a distinguishable permutation. The solution is to use the multinomial function. If you've seen this function before, to use this, we first count up all of the letters as if they were distinguishable. In this case, there are 11 letters, so we put that in a factorial and put that in the numerator. Then we find all the multiplicities. In this case, M has multiplicity 1, I has 4, S has 4, and P has 2. We put factorials on each of these and write that in the denominator. So there you have it. This is the solution. However, the book hasn't discussed the multinomial, and it does discuss the multinomial in a later section, so it's likely the author doesn't intend for us to solve the problem this way. We could instead solve the problem by first choosing the location of the M. This can be done in 11 different ways. Next, choose the 4 locations of the I's, which can be done in 10 choose 4 ways, since one position is already occupied by the M. Finally, we choose the positions of the 4 S's in 6 choose 4 ways. Automatically, the unchosen positions are filled with P. If we compute the two solutions, one using the multinomial function and the other using a sequence of choices, we should find that the two solutions agree.
Next, problem 1-111 asks, given a bag with many marbles in each of 4 colors, count the ways to select 12 marbles. Count the distinguishable ways to put 12 of them in a row. The first part is a direct application of stars and bars. I like to imagine placing 12 objects in 4 bins and finding all ways of distributing objects to bins. The stars and bars formula tells us that we can do this in 12 plus 4 minus 1, choose 4 minus 1 ways. In the second part of the problem, we care about the order of the colors. Therefore, we cannot count in the same way as before. Instead, we can start by drawing each position that the marbles could be in. We can then choose a color for each position. This can be done in 4 to the 12 ways.
For the last problem in this video, we imagine that there are 7 million people in New York City. Each has a jar containing 100 coins, and each coin is one of 5 types. The question is whether we can give a distinct jar configuration to every person. At a first level of analysis, this is a pigeonhole principle problem. If we imagine lining all of the people in the city in a row and assigning the first person a jar configuration, for the next person we want to assign them a different jar configuration, and assign the third person a configuration distinct from the first 2, and so on. If we run out of people before jar configurations, then every person can have a distinct configuration. But if we run out of configurations first, then after we have used up the last distinct configuration, the next person must be given the same configuration as someone before them. So all that we have to do is count up how many configurations there are. This is an application of stars and bars, with answer 100 plus 5 minus 1. Choose 5 minus 1. When you enter this in a computer, the result is less than 5 million, so you run out of configurations before people. Therefore, it is not possible to assign each person a distinct configuration.